Now, today we are going to start a new lecture series on the topic of distillation operation. Now, in the first part of this lecture series, I am going to discuss about the pressure drop of vapor when it passes through a tray in a distillation column or absorption column or a stripping column. I mean, in general, any tray column. What happens when vapor passes from the bottom of a tower or a column and it goes to the top of the tower, then its pressure reduces. Now the total reduction of the pressure is called the pressure drop of the tower. Now this we need to determine. Why? When we design any column, what happens? We first determine the pressure of the top of the tower, and if we could find the pressure drop of the tower, then we can calculate the pressure of the bottom of the tower, and based on that pressure we can calculate the bottom temperature. Now based on that bottom temperature and pressure we can design our reboiler, or in any operation we can determine what will be the bottom temperature and pressure. Now how we determine the pressure drop of the tower? What we do is we actually determine pressure drop of vapor for a single tray, and then we multiply with that pressure drop to the number of trays, and that will give total pressure drop for the tower. And for that reason we need to determine tray pressure drop. This is the one motivation for this lecture. And another reason is what happened in any distillation column, there we find many operational instabilities like weeping, flooding, entrainment. So we must check the pressure drop per plate to make sure that our column is operating properly. I mean, how pressure drop is linked with all these operational instability, that will be clear in this lecture and in the subsequent lecture. But for right now, we should understand that we need to understand pressure drop per plate for a thorough understanding of operational instabilities like weeping, flooding, entrainment, and all those things. So with this brief motivation, let us start our discussion about pressure drop of vapor when it passes through a plate or passes through a tray. Now what happens if I need to determine pressure drop for vapor when it passes through a tray, then we had to actually figure out what are the restrictions of vapor flow when it passes through a tray. Because if there won't be any restriction, then there won't be pressure drop. Though it will be slight variation of pressure due to potential energy changes, but that will be very negligible. So if vapor pressure is reducing, it means it experiencing some restriction or some friction losses. So we have to figure out what are those restrictions. So suppose vapor is flowing from the bottom of this tray to the top of this tray, then what happening in the path of this vapor flow, first find there are different sieves or holes or orifice, and these orifice or hole will provide a restriction of vapor flow, and because of that restriction pressure of vapor will reduce. Now this pressure drop due to orifice or the tray perforation is called dry tray pressure drop and is represented by HD. Why call it dry tray pressure drop? We call it dry tray pressure drop because this pressure drop will take place even if there is no liquid on the tray. Okay. Now what happens when vapor has crossed this tray and has reached here, then it found that there is a head of liquid or there is a pool of liquid, and it has to go through this pool of liquid. So this pool of liquid will also provide some restriction of vapor flow, and because of that there will be pressure drop. Okay. Now because of this head of liquid or hold up of liquid, the pressure drop of vapor is called hydraulic tray pressure drop, as represented by HL. L represent here liquid. Now what will be this hydraulic tray pressure drop? This hydraulic tray pressure drop can be think of in reverse direction. I mean the pressure of vapor here and the pressure of vapor here will be having some difference, and that difference can be calculated if I know the pressure here, and then if I want to find pressure here, then what I will have to do, pressure up at this point plus density of liquid times G times height of liquid. That will give the pressure of vapor at this point. It means when pressure have passed through this liquid, it has loose pressure corresponding to the height of liquid. Okay, so hydraulic tray pressure drop will be equivalent to clear liquid height on the tray. Okay, now apart from this pressure drop, there is another pressure drop of vapor due to surface tension of liquid, and that is referred as residual tray pressure drop, and it is also represented by H sigma, where sigma represent here surface tension. So when vapor passes through a tray, it experiences three component of pressure drop, and the total tray pressure drop will be sum of these three component of pressure drop. Okay, now in general, in literature or in any book of distillation, what we find that the pressure drop of vapor in a distillation column is usually given in terms of height of clear liquid. I mean, we do not provide pressure drop in pressure unit, rather in terms of height, I mean head of clear liquid. So if I want to convert this pressure drop in terms of pressure unit, then we have to multiply by density of liquid times G times this H. So we have to take density of liquid, and that density we have to take clear liquid density. That should be very clear. Okay. Now let us discuss all these three components one by one numerically. Now the first component is dry tray pressure drop. Now this pressure drop is taking place because fluid or vapor has to pass through different sieves or holes on a tray. Now if I want to figure out what will be the pressure drop because of this orifice, we can think of pressure drop through a orifice, and we have gone through in our course when we have done our engineering wherever, that whenever a fluid passes through a orifice, its pressure reduces, and that pressure reduction can be calculated by energy balance between the upstream of the orifice and the downstream of the orifice. For example, this expression I have taken from the book McCabe and Smith, where they have calculated energy balance between the 2 point A and B, and based on that we have they have calculated the flow of fluid through the orifice. So if I am interested in pressure drop instead of flow, then what I have to do, we have to rearrange this equation, and delta P will be in one side and other terms in another side. Okay, so based on that we can calculate pressure drop through the orifice. Now since I have to give pressure drop in terms of clear liquid head, not in terms of pressure unit, then I can equate pressure drop in terms of density of liquid times G times clear liquid head. So after these arrangement, we will get this expression, this G and density of liquid, because of I have written pressure drop in terms of clear liquid head. So we can see that dry tray pressure drop usually increases when velocity increases. Here U naught is vapor velocity through hose. Now if vapor velocity through hose is in terms of meter per second, then 1 by 2G can be written or can be calculated is equal to 51 if HD is in millimeter, and this is very easy. Similarly, if I want HD in terms of inches, then it will be 0.186. Okay, now this rho V is vapor density, rho L is liquid density. Now this C naught is called orifice coefficient. What happens when we have balanced our we have done energy balance between the upstream of the orifice and the downstream of the orifice, then we have also used our continuity equation to arrive this expression, and continuity equation is basically A1 V1 is equal to A2 V2, so that will be basically a constant, and that is included in this orifice coefficient. So orifice coefficient basically depend on the fractional hole area. I mean here fractional hole area is the ratio of total cross sectional area of the hose to the column cross sectional area, and it also depends on the tray thickness to hole diameter. So in that way we can calculate dry tray pressure drop. Now let us talk about hydraulic tray pressure drop. Now we have discussed about that hydraulic tray pressure drop basically correspond to the height of liquid on the tray. So we have to figure out what will be the height of liquid on the tray. Now basically height of the liquid on the tray will be weir height and plus crest height. I mean the liquid is flowing over the weir and it will form a crest. So if I want to figure out what is the height of liquid on a tray, then basically we have to figure out what will be the crest height, because weir height we already know. Okay. Now this crest height is basically calculated by famous Francis equation, and that Francis equation is basically for fluid flowing over a dam. I mean when fluid flowing over a dam, then it also make a crest, and that crest height is calculated by basically a Francis equation, and that is given by this equation. Here we can find that this height of crest will increase when volumetric flow rate of liquid increases. Also this height of crest will decrease when length of the weir will reduces, and that seems logical to us. Okay, now here the height of liquid over the weir is clear liquid height, because we have taken QL is volumetric flow rate of clear liquid. So that should be very clear right now here. Now what happens, actually the height of crest will in reality will be much higher than this, because this is clear liquid height, but actually the liquid on the tray is in terms of froth. I mean this is a vapor liquid, is in dispersed phase. So the height of actual crest will be much higher, or reversely the liquid on the tray is in terms of froth. It means the clear liquid on the tray, if I will figure out the height of, if I have to figure out the height of clear liquid on the tray, then that will be the crest height in terms of clear liquid, and plus this weir height should be multiplied by adhesion factor. I mean adhesion factor means how much vapor is going there. If more vapor is going there, the density of liquid will be much less, and it means height of clear liquid will also be very less. So are you understanding what I am going to what I am trying to clear that? If I have to calculate pressure drop because of this liquid head, then I have two options. I have to know the actual froth height and the actual density of the liquid, or I have to know actual clear liquid height correspond to that froth height, and then we can multiply by the density of clear liquid. So since I have defined my pressure drop in terms of clear liquid height, so I have to take clear liquid height correspond to this froth height. So this HOW is already I have taken as a clear liquid height. So similarly correspond to weir height, I have to calculate clear liquid height due to froth. So that can be calculated when we multiply this height, weir height, by some adhesion factor. So in that way the height of liquid, I mean clear height of liquid height will be adhesion factor into weir height plus HOW, that is height over the weir, that is crest height. But here in McCabe and Smith they have multiplied HW plus HOW times beta. So here this beta having some other meanings, but in the process equipment working guide to process equipment by Lieberman, they have given the hydraulic tray pressure drop is equal to adhesion factor times weir height plus this crest height in terms of clear liquid. So that will be my hydraulic tray pressure drop. So if I will put if I want to determine the pressure drop of vapor when it passes through a tray, and if I put at one tapping here and another tapping here of a U-tube, then I will get a difference of pressure in these 2 points I mean below tray and above tray, and that will be equal to total liquid height, I mean total pressure drop HT in terms of clear liquid, because the inside the U-tube there is a clear liquid. Similarly, if I want to calculate hydraulic tape pressure drop, then I have to put one tapping here and the another tapping in the I mean the clear vapor zone, I mean vapor zone of the tray. And if I will do this, then I will get HL, that is hydraulic tape pressure drop, and you will find that this is even lower than the wear height, because though height on the liquid is much higher above the wear, but if we will calculate in terms of clear liquid height, then it will be much lesser, I mean even lesser than the wear height. And this is a usual phenomenon. In general, it finds that the hydraulic tape pressure drop is smaller than the wear height. Okay. Now, when vapor passes through the liquid pool, then what happens? Vapor is coming below the tray, it has passed through the orifice, and when it passes through the orifice, it emerges out as a bubble. So vapor bubble is rising through the liquid, and we know that whenever a vapor bubble is available in the liquid, then there is an excess pressure inside the bubble, and this we have studied in our school. So it means the pressure inside the bubble will be higher than the liquid pressure, and that difference we know that will be equal to 2 times surface tension divided by radius of vapor bubble, or 4 times surface tension divided by diameter of vapor bubble. Now, since the bubble which is rising through the liquid, its diameter is increasing, so if I take average of the diameter, then we found that it turns out to be 6 times surface tension divided by diameter. This is given in Travel, Cedar and Henley, and all these books. So what happened? The bubbles which is having higher pressure has lost that higher pressure when it crosses the liquid, because now the vapor is in continuous phase, there is no bubble, so there is no extra pressure, there is no excess pressure. So we can think of that pressure has been reduced because of this surface tension. So that pressure reduction can be calculated by this formula, where I have taken again this residual pressure drop in terms of height. So, but what we have found that this residual tape pressure drop is much lesser correspond to the dry tape pressure drop and hydraulic tape pressure drop. So because of that reason, many author has neglected this residual tape pressure drop. In general, we find that dry tape pressure drop will be higher than hydraulic tape pressure drop, and hydraulic tape pressure drop will be much higher than the residual tape pressure drop. So we can neglect residual tape pressure drop. Okay. So we have discussed about the hydraulics of tray, how pressure is reducing when it passes, when vapor passes through a tray. Now let us discuss about when weeping will take place in a column, in a tray column. So let us first discuss about what is weeping. Weeping is, what is the normal path of liquid in a tray column? Normal path of the liquid is, liquid will flow from the upper downcomer of a tray, and it will pass through the tray, I mean cross flow of liquid will be here on tray, and it ultimately drop in the lower downcomer. Now this is the usual or normal path. Now instead of liquid flowing through the downcomer, some part of the liquid, if I start dropping, or if I start flowing from this hole to the lower tray, then that phenomena is called weeping. I mean ideally all liquid should pass through this tray and drop inside the downcomer, but if some part of the liquid is going through this path and some part of the liquid start dropping through this hole to the lower tray, then that phenomenon is called weeping. Okay. Now this basically reduces the efficiency of the tower. Why? Because ideally when when liquid has passed through this much distance, then it has gone through contact with vapor up to from here to here, and it has so the liquid has had residence time much higher for vapor liquid intimate contact. But when liquid will directly drop here to the bottom tray, then it won't be having any intimate contact with the vapor, and another there won't be having residence time for the liquid to pass through this much length. Okay, so what will happen? The mass transfer between the liquid and vapor will be much less, so efficiency will be drastically reduced. Now there is another phenomenon called dumping. In that case, instead of liquid going through the usual path, I mean through the downcomer, all of the liquid will start dumping, I mean will start dropping from this hole. So none of the liquid is passing through the downcomer, all of the liquid has been started passing through the holes, then that phenomenon is called dumping. Now let us discuss what will happen when will happen weeping based on our tray hydraulics. Okay. So to figure out weeping, let us figure out what will be the pressure profile of a tray column, and based on that we will figure out when the liquid will start dropping through this hole. So suppose pressure above the tray of vapor above the tray is P1 and Y correspond to the hydraulic tray pressure drop, then the pressure at this point will be P1 plus Y. Now if X correspond to the dry tray pressure drop, then pressure at this point, I mean below the tray, will be P1 plus Y1 plus X. So it means the pressure drop across the tray will be Y1 plus X, and it will be higher than the hydraulic tray pressure drop. So it means ideally pressure of vapor will be higher than the liquid pool of weight of the liquid pool. So liquid should not drop. So earlier what I usually thought when weeping will take place, when this dry tray pressure drop becomes extremely low to the Y, then the pressure will be higher at the bottom of the tray, but that excess pressure is much lesser. And if in that case there is a high difference of liquid, I mean usually what happens when liquid exit from this downcomer, at that point liquid height on tray is higher than the when liquid exit through this sphere. So there is a liquid head gradient, and because of that liquid flow in this direction, and that ideally that gradient should be very small. But if there is a liquid head gradient, and if this vapor pressure of vapor below the tray is very less excess than the weight of liquid, then in that case in some part of liquid where liquid height is high, in some part of liquid will start dropping, because that part weight of the liquid can't be balanced by this much excess pressure. That I used to think. So what will happen in that case, liquid will start dropping from this part and vapor will start passing through the lower liquid height path. Okay, and a channeling will take place. So when liquid vapor will pass through this tray, then here a pressure imbalance will take place and vapor will start flowing in this direction. So there will be vapor cross flow and there will be liquid cross flow. So that will significantly reduce the efficiency. And this concept, which I used to think, was confirmed by even in the McCabe and Spieth. In that book, it is written that the condition of called weeping is more likely to occur if there is a slight gradient in liquid head across the plate. And with such a gradient, vapor will tend to flow through the region where there is less liquid and therefore less resistance to flow, and liquid will flow through the section where the depth is greatest. Okay. Now, when I read this was so far so good, but what happened when I read the distillation book by the famous Henry Kister. He is very famous in distillation field. He has written 3 books: distillation design, distillation operation, and distillation troubleshooting. And also in the book by Lieberman, he is also very famous process engineer. I found that they have written that weeping will take place when X become less than Y. I mean when dry tray pressure drop become less than hydraulic tray pressure drop. So that was not clear. Through the tray hydraulics or through the pressure profile. So, for example, in the Henry Kester distillation design book, it is written that weeping takes place when the liquid head on the tray exceeds the pressure drop that is holding the liquid on the tray. Now, if here pressure drop will be total tray pressure drop, then total tray pressure drop will be always higher than the liquid head. So, this pressure drop can't be total tray pressure drop. And this I also confirmed by emailing him, by an email with Henry Kister. I mailed him by asking that what he mean by pressure drop, whether it is dry tray pressure drop or the total tray pressure drop. So he replied that it is actually dry tray pressure drop. So he thinks that liquid head is balanced by dry tray pressure drop. And this is also confirmed in the later part of that book, where he has calculated the weeping point when the liquid head becomes the equal to dry tray pressure drop plus this surface tension. And here actually F is aeration factor. So according to Henry Kester, it is the dry tray pressure drop which balances the liquid head. Similarly, in the book Working Guide to Process Equipment by Lieberman, it is written that when the dry tray pressure drop is significantly less than the hydraulic tray pressure drop, the tray will start to leak or weep, and tray efficiency will be adversely affected. So though here he has written that dry tray pressure drop should be significantly less than the hydraulic tray pressure drop, but when I emailed him that about this pressure profile, then he replied actually dry tray pressure drop holds the liquid. So basically they are the expert in this field, so we will accept their proposal, their understanding. It is also confirmed in the book Cedar and Henley. Here in that book also it is written that weeping point can be calculated when dry tray pressure drop becomes equal to the hydraulic tray pressure drop. So from here onward we will think that dry tray pressure drop basically balance the hydraulic tray pressure drop. Okay. So based on that understanding, if my dry tray pressure drop is balancing my hydraulic tray pressure drop or the weight of the liquid on the tray, so based on that understanding we can find what will be the weeping condition, when weeping will take place. So weeping will take place when dry tray pressure drop become lower. So dry tray pressure drop basically will be proportional to the vapor velocity. So when vapor flow rate reduces, then weeping may take place. Similarly, if if vapor flow rate to the tower is same but the fractional hole area increases, in that case also vapor flow rate through the orifice reduces and the dry tray pressure drop reduces. So based on this, we can call that the lower limit of operation. If I want to calculate at what lowest possible volumetric flow rate of vapor we can operate a column, then that lowest possible limit will be decided by the weeping condition. If we will reduce further volumetric flow rate, then weeping will start take place. Similarly, weeping may also take place when liquid flow rate will be high. In that case, what will happen? Liquid flow rate will high, then height over the weir HOW will be high. Dry tray pressure, hydraulic tray pressure drop will increase and it may exceed the dry tray pressure. Similarly, taller weirs, if my height of weir will goes high, then also hydraulic tray pressure drop will increase and it may go beyond to the dry tray pressure drop and the weeping may take place. So if I want to avoid this weeping condition, during design condition we may reduce the whole fractional area so that the vapor velocity will usually remain the higher condition and weeping can be avoided. But again, when whole area will be reduced, then the upper limit of vapor will also reduce, because in that case higher vapor velocity will be through the orifice and that will lead to another problem called entrainment. So we are going to stop this part here. And in the next part we are going to discuss about the flooding. What are the different types of flooding in a distillation column or any tray column can take place? What is the mechanism and how can we avoid flooding? That will be the topic of the second part. Thank you.